So it's my great pleasure to introduce Max Gronke, if I pronounce it correctly. He is a Hubble Fellow at UC Santa Barbara, that's where I know him, and he's with the GHU. He is an expert and a theorist of the CGM, especially the destruction or survival of cold gas. Before that, he did his PhD in Oslo, in Norway, where he worked with Mark Dijkstra on Lyman-alpha radiative transfer. So let's enjoy this talk.
Thank you, Stephanie. And thanks a lot for inviting me and hosting me here. It's a pleasure to be here, and thanks a lot everybody for coming. I understood that this department is quite observationally focused, so I try to, I'm a theorist, and I try to, motivate the questions that govern my research. As Stephanie said, I was at UCSB before in beautiful Santa Barbara, but I'm just moving to Johns Hopkins at, well, Baltimore. Well, the title of my talk is The Struggle of Cold Gas and Hot Halos, and as an intro, I thought I'd just go through all the terms here. So let's start with hot halos. We know from our theory of structure formation, right, that dark matter clustered first in the early universe and formed these dark matter potentials, where then baryonic matter streamed in, and because the potentials are so deep, a lot of this gas gets shock heated, very hot, and just some of this cools down and settles and forms galaxies and stars and all the things we know. Now, observing these hot halos, this hot gas around galaxies, which we think is around all or most of the galaxies, is quite hard, because observing an X-ray is quite hard. So we can only see it if this gas is extremely hot. So just for the biggest clusters or big galaxies. So you see an X-ray image here from Chandra, where the purple shows you this really hot gas around this cipher, this massive galaxy here. This is where we can see it. So more recently, though, people have also observed this gas around galaxies with different methods, namely absorption line studies. And so the COS instrument at HST was a real revolution there, because what you can do is use some really bright source, often a quasar or a bright galaxy in the background, and take a sight line, and then through these absorption slides you can study what happens in these hot halos. And what people have found, many things people have found, and Stephanie is an expert in this, and I don't want to go into so much detail. I want to take one step back and just ask, one of the main things people have found is that there's quite a lot of cold gas out there in these hot halos, and that to show that, I show you here this plot from Prochaska et al., where here on the x-axis you have the impact parameter, so how far away you look from these galaxies, and on the y-axis is the neutral hydrogen column density. So you see even far away from the galaxy, you see significant amount of neutral hydrogen, which is cold gas, right? So we know now that we have quite a lot of cold gas, 10 to the 4 Kelvin or so, in these very hot halos, 10 to the 6 or even hotter. And this is surprising, and that's basically the question I want to address in my talk. Now, many still ask, why, I'm interested in galaxies, why should I care about all this gas, around galaxy? Why is there all this hype about, people now call it circumgalactic medium? But, the way I see it as from a theory standpoint is that, it's like the goldfish in a glass, right? If you want to study, the life and intake and outtakes of this goldfish, you can study the goldfish in great detail. But you also know that everything the goldfish eats has to go through the water, right? So you can study also the water around the goldfish, and that's quite nice because, while the ISM and the galaxies are highly complex system, this gas around these galaxies is somewhat less complex, so it's a nice probe to study our theory of galaxy formation and evolution. Now, especially cold gas in this circumgalactic medium, I think is quite interesting because we know that first of all there's cold streams that penetrate into these hot halos up to redshift 2 or so that controls future star formation. And why we think most of the outtake of galaxies is governed by hot gas, supernova, AGN feedback. Inside this hot gas is still pockets of cold gas, and we're actually quite lucky for that because otherwise tracing this outflow is quite hard. So we use this embedded cold gas as a proxy and as a tracer for feedback. So by studying cold gas in the CGM, we can study how galaxies obtain gas and how they eject gas. Okay, and so I want to just group my talk into the 3 main questions I already alluded to a little bit, right? So we have this extremely hot halo, millions of degrees, and then we have some 10 to the 4 Kelvin gas in there. So the first question is really, how did the gas get there, right? You would be surprised if you see, I don't know, a snowman in lava. It would be highly surprising, but one maybe even more surprising thing would be if you look an hour later, the snowman is still there, right? So how does this gas survive? It's the second question I want to address. And the third question is, what is the structure? And I will come back to that, why I think that might be an interesting question. Now the thing is that all these 3 questions are connected, and I hope I can convince you of that and during my talk. Let's start with the last question, what is structure? And just to motivate this question a little bit more, observations can already tell us something about the structure of this cold gas in the halo. Now I showed you this plot before, again of the neutral hydrogen column density as a function of impact parameter around galaxy. And you see only very few sidelines here, they haven't detected any neutral hydrogen. So we already know, no matter where you look, you will find cold gas. So it has a large aerial covering fraction, right? Now what you can go on and do, and many people have done that, you can do photoionization modeling if you have several transitions, and what you will then also get is a number density, right? So with a column density and a number density, that already gives you some kind of scale, and many people have done that, and the scale, they come up with cold gas is quite small, less than 100 parsecs. People say 30 parsecs. So that's tiny, right? You have these hundreds of kiloparsec halos, and there's some little droplets of cold gas embedded in the halo, and they're everywhere. So that's quite surprising, and that's what observations tell us. Oh, by the way, this is just an upper limit too, because we as observationally through these sidelines it's hard to probe. Is it one blob or is it 2 behind each other? So it's just an upper limit. This 100 parsec from these models. Now, these small scales, they put our models of galaxies in front of immense problems, right? Because nowadays we rely on big computer simulations to make predictions and to test some theories. And in order to manage this range of scales that astrophysics has, right, from small scales in the ISM to large cosmological scales, the computational techniques people use is so-called adaptive techniques. And I'm sure many of you have heard of them. So you have smooth particle hydrodynamics. Oh, you don't see anything. Oh. It should be. So you have smooth particle hydrodynamics where you put a lot of particles in this dense region in the inner disk. So I put a lot of dots here. And then you have way fewer dots in this halo. Or similarly, if you're Eulerian approach, you can have what's called adaptive mesh refinement. It's a very similar approach. You just you have your grid of where you solve your hydrodynamic equations, right? But then you put many more grid points in this dense region in the disk. But that means several things, right? So while nowadays we can achieve parsec resolution in the ISM or even better, out in the CGM we still have worse than kiloparsec resolution. And clearly that's a problem if we want to study structures that are less than 100 parsec or so in the CGM. So more recently, many people try to address this problem. So there's been groups, for instance, Cameron Hamels, Freke van der Voort, there's Molly Peoples. They all do a similar approach. And what they do, instead of using the normal AMR, adaptive mesh refinement, they put a uniform grid also here in the CGM. So this is a result from Cameron Hamels, where he puts, this is the normal AMR result, and here he puts a grid with 500 parsec resolution also in the halo. And just visually you can see, so this is the neutral hydrogen quantum density. Just visually see, it changed quite a bit, just putting more resolution. Basically the same result was published a bit earlier by Freke van der Voort. There she does, this is in blue, you see the standard simulation. In green, she puts a little bit more resolution, 2 kiloparsec resolution out in the halo. And in red, highest resolution, 1 kiloparsec grid out in the halo. Neutral hydrogen quantum density as a function of radius, and you see, the higher the resolution, the more neutral hydrogen she finds in the simulation. And quite significantly, this is, more than an order of magnitude different. But one other thing, which is, I think is even more worrying, is that it's non-convergent, right? So the more resolution you put in the halo, the more cold gas they find. And actually there has been some recent work by Freke who, they increased the resolution even further, and you can see in this plot they compare to actual data, and they say, it's maybe more consistent in this red line compared to their original blue line. But now they ran some more simulation, they increased the simulation even further, so now they have too much neutral hydrogen compared to the data. So what I take away from this is just that, it's just a non-convergent result, which I think is highly boring. If you want to use this simulation to, check, say, our feedback mechanisms, check our basic theory, we use results there to compare to data. We don't know if it's, due to the implementation of certain physics or just due to convergence issues, essentially. So this is why I think, what we have to do is we need to know the scale for this cold gas in the CGM. Once we know the scale, we can, have the resolution and resolve this scale, and then we are happy. So that's why I, asked this question: what's the scale of this cold gas in the CGM? Okay, now the other reason why I think the scale of the cold gas is quite important has something to do quite differently, and that is it's important for radiative transfer. So this is a plot of several Lyman-alpha spectrum. For those of you who don't know, Lyman-alpha is the first transition of neutral hydrogen. It's a resonant line. That means Lyman-alpha photons scatter many times before they escape the galaxy. And nowadays it's used in astrophysics, as a detection method, but also a probe for gas in very distant and nearby galaxies. And so what I've done here is I computed a bunch of Lyman-alpha spectrum with a fixed hydrogen quantum density of a system. And all I did is I stratified my medium more, right? So I put more clumps in. So I might go from this picture to that picture, and you see visually that the spectrum is changing quite dramatically. So also here again, we need to know which scale this cold gas clumps have in order to run radiative transfer through our simulations and then get the correct results. Now, the thing is that I love Lyman-alpha. It's my favorite line, and I'm very happy to chat with any of you about resonant line transfer. But I won't mention it anymore in my talk. Just as a side note, these kind of spectra where you have this dip in the middle of the line, that's more consistent with observations. So, in fact, this fog of clumps might be more consistent to what, similar to what I said before, what is out there in the real world. Okay, now I think I have, motivated well enough all my questions I want to answer in this talk. So let's go and answer them. And let's start with the first one. How did really the cold gas get there? So I think we have two options, right? We either create the cold gas there or we bring it there. And I will discuss both of these options, but I start with the first one. So let's bring the cold gas into the CGM. And I already drew this cartoon before where this galaxy resides in the dark matter halo. So you can either have cosmological inflows that bring cold gas into the CGM, or you have outflows. And while mathematically or from the problem they're quite similar, out of brevity, I will just discuss the outflow case. So, outflows. Galactic winds. This is a picture, composite image from the galactic wind from M82, a nearby starburst galaxy. And what you can see here, this color coding, is different, bands. So in blue, here light blue, you have this, again, this hot X-ray emitting gas. And co-spatial, you have, again, much colder gas, 10 to the 4 Kelvin H-alpha emitting gas. So we know that galactic winds are multiphase, and that's not just the case, in this galaxy, but in many more. Now, there's been recent work, for instance, by Kate Rubin, but many other authors have basically agreed that at least in some from galaxies, galactic winds are ubiquitous. So, they bring something at least into the CGM. And, if you ask how fast are these winds, there's this nice review article by Silva Bayur, and here he has this plot, where he shows, it's hundreds to thousands of kilometers per second. That's what we're talking about, just as a setup for these galactic winds. Okay. Now, as a theorist, what I do is I try to, zoom in here and draw an extremely simple picture of the setup. So here we have our multiphase galactic wind. So what we have is a hot wind with a certain number density and a certain speed, penetrating this cold gas cloud, also with a certain number density and a radius. And what happens is two things, right? So first of all, this hot gas pushes this cold gas and tries to make it move. But also what you have is hydrodynamical instabilities that will try to destroy this cold gas. Okay. So if you write down how fast can these hydrodynamical instabilities destroy this cold gas, so it's mainly the Kelvin-Helmholtz and the Rayleigh-Taylor instability, there will also be a shock crossing through your cloud. Interestingly, all these instabilities occur at the same time scale. So that is, the overdensity, which is the number density of your cloud divided by the number density of the wind, to the 1/2 times the radius of the cloud divided by the wind speed. Now, how long does it take the wind to, accelerate the cold gas to a speed similar to the wind speed? There you have the same fraction of the radius divided by the wind speed, but this time times the overdensity. You already see probably where I want to head with this, right? Because if we take our observations from before and we assume pressure equilibrium, we know that the overdensity is at least a factor of 100 or so. So the cold gas is at least a factor of 100 denser than the surrounding medium, and therefore your acceleration timescale is much longer than your destruction timescale. So in other words, cold gas should be destroyed and not fast moving. So why do we see it moving in these multiphase galactic winds basically everywhere? And that is, many people don't like equations, so that this is not just some equations written down. It's actually true. I show you some results from hydrodynamical 3D simulations. So this is a slice through an Athena simulation, where you see the cold gas here, that's density color-coded. You have the time in numbers of cloud crushing timescales, the cold gas mass, and the wind speed between cold and hot medium. And so you see very nicely here the Rayleigh-Taylor instability occurring. Here you have some Kelvin-Helmholtz now, classic, and the cold gas mass is indeed going down. If you are wondering why is the cold gas not moving, this is because the reference frame of the simulation is in the reference frame of the cold gas. So basically the camera is moving along. And just let's try, that's already. Yes, after a few cloud crushing timescales, there's no more cold gas left. And that problem is in fact a quite old problem. It's called the entrainment problem. There was a nice paper in the 90s by Klein et al., Klein McKee, and they already wrote down these timescales, and they asked, how come we see all this cold gas fast moving, but obviously it doesn't work. One suggestion they had already back then was, well, maybe cooling might help. Because if you cool hot gas, you replenish your cold gas, and probably that helps. So what people have done since was to run simulations, 3D simulations, modern simulations with cooling. There's a plot I show from Scanner, Kieko, and Rubin, but there's also Evan Schneider and Cooper et al. There are many people who ran these kind of simulations. And I just showed this example from Evans Scandia's work. So as a function of time, you have the cold gas mass left, and you see after a few cloud crushing timescales, not much cold gas is left. So that led to this very nice paper by Dong Sang, and their initial point of this paper was to ask, after say 3 cloud crushing timescales, I still have 50% of my gas left here. Maybe that's enough to explain all the observations. So they, went through many observations of Euler's and so on, and tried to compare how much cold gas mass you have in the wind versus how strong is the wind, etc. But you see already their conclusion in the title that it didn't work, it didn't fit. So this classic picture of entrainment, they said, is in trouble. And yes, so that was the state. We basically revisited this problem. And our initial question was to ask, so where does the cold gas really go to, right? It's not actually destroyed. You don't destroy the molecules, you just mix it away with the hot gas. And if you ask yourself, what are the properties of this mixed gas, you can go and read this paper by Begum and Fabian. It's about the theory of turbulent mixing layers. And what they find is that the temperature of this mixed gas is in fact the geometric mean of the hot and the cold temperature. So given by this term, if you demand pressure at equilibrium, that gives you a number density, which is also given by the geometric mean. What does that help you? Well, with these two numbers, you can compute the cooling time of your mixed gas. And what you'll find is that your cooling time of your mixed gas is longer than your cooling time of your cold gas by a factor of 10 or so, clearly because the gas is less dense, but it's not that much longer. So now in order to survive, you can ask, if I can cool my mixed gas faster than I can destroy my gas cloud, so basically I always have a replenishment of new cold gas, then my gas cloud should survive. Okay, so movie time again. This is the movie we've seen before where this critical ratio is larger than unity, and here it's smaller than unity. And you can see that initially we drop, but now our cold gas recollects in its tail, and it cools out, and we end up with more cold gas than even we started with. And whereas this other one we saw before, it's been destroyed. Okay, so that's great. It seems to work. You can show that maybe a bit more quantitatively. Here as a function of time, the cold gas mass, and the color coding shows you this critical ratio of T cool mix over T cloud crush. Populate this parameter space, and you see roughly it works. All the stuff that's red, the cold gas mass goes down. All the other things where this ratio is smaller than unity, we create new cold gas. One advantage I just want to mention from this thing is that if you cool out this fast-moving hot gas, you also have a momentum transfer, right, to your cold gas. So you don't have to push it that hard anymore. That's also why that helps. Okay, so that's basically how to survive, cold gas in the wind. You just have to have this critical ratio be smaller than unity. And one important thing is also, if you want to simulate that, you have a long enough box because all the action here happens in the tail. And that's really why a lot of people haven't seen that yet, because often when you simulate these things, you try to, save computational time, so you make as small box as possible. But, oh yeah, one thing I want to quickly mention, I don't know how many people here are interested in magnetic fields, but we know the plasma is highly magnetized. So if we imagine, our wind, there is a magnetic field, a large-scale magnetic field, which is orthogonal to the wind, and you have some other tangled magnetic field in this cold gas. What will happen, is that these magnetic fields will bend around, and you build up some magnetic pressure here, which is nice because you can push the gas more, right? Which is called magnetic draping, and then, but it also prevents mixing. And while this usually is a good thing, right, it also protects our cold gas. In our picture, it might not be so good, right, because we want some mixing in order to cool out. But I don't want to spend too much time on this, so I just show you, a movie, and to convince you that the mechanism still works. So this is, I think, with beta of 1 and 1, for those who know, it's like a fairly strong magnetic field. And you see it works, but you also see that you get a quite different morphology. And what happens there is that the cooling, it compresses magnetic fields inside the cold medium, so you end up with a magnetically pressure-dominated cloud, which is quite interesting. Yeah, so this is for different betas. Again, the cold gas mass is a function of time, and you see, for large betas, the red line, you see that, yeah, the mixing is going down, so you end up with less cold gas mass, but you're still more than you started. Now there's one thing that is not quite right in this whole story I've been telling you about mixing and then we cool out. And maybe you already spotted it, it's strange both in the magnetic field and the non-magnetic field case. And so the strange thing really is that, the mass growth here, it doesn't cease even when the cloud is entrained, right? So if you look here, basically we don't have any relative motion anymore between hot and cold medium, but our cold gas mass is still going up like crazy. And that's a bit strange, right? Because if there's no relative motion, there's no shear, there shouldn't be much mixing. But I can show you here, as a function of time, I showed you this many plots many times before. If you try to do a derivative here, it's pretty constant. Or I can just take you the derivative for you, so that's the mass growth rate, as a function of this relative motion of hot and cold gas. But if you have less motion, it doesn't go down, it in fact flattens out. And so how come that you have this constant mixing, even there's no relative motion anymore? And one thing that helps to look at is the slide through the emissivity. So that's where this cooling actually happens. And so you see here, once we're entrained, it's still a lot of stuff is happening, right? You have these waves that reflect, and the whole cloud is pulsating. So these pulsations I can visualize when I take, that's the change of volume as a function of time. So you see you have these pulsations in total volume. And these pulsations are, constantly induce cooling, which then creates some underpressure, which draws a new hot gas. So the cloud keeps on growing even if you don't have any shear. Now, looking into this emissivity plot a little bit closer, so this is from our high resolution simulation, where again this is the emissivity, and you see here basically all the cooling happens on the surface between hot and cold medium, right? And that's highly boring, right? Because even if this is happening, even in our highest resolution simulation, it's just one cell thick. How come, I talked before about how important convergence is, but how sure are we that these results are converged? So, we changed the resolution between 8 cells per cloud radius and 64 cells per cloud radius. And we find that the mass growth rate is quite converged, and that's strange, right? If all the cooling happens in this one cell thick layer. But because what we would expect, that's from a grad student at UCSB, Frank Tan, and what he has done some simulations where he looked at just one of these layers around the cloud. So he just simulated this little piece, this one mixing layer, and he could really go crazy with resolution because that's just 1D simulation. So changing the resolution by 4 orders of magnitude. And what you find here, that's the mass growth rate as a function of resolution. You only converge once you reach the field length that's set by thermal conductivity. But in our case, we're much bigger, so we shouldn't really be converged. But we are. So how come that? And that's also due to these dynamics, because these pulsations, they set another length scale, which is larger than the field length, and we resolve that one. And I can prove you this by having a cloud which I perturb a little, and a cloud which I don't perturb a little. And so this is the mass as a function of time. For the perturbed one, you see it changes quite a lot with resolution. For the non-perturbed one, for the perturbed one, it doesn't change that much. And you see again, the perturbed one has these oscillations, whereas here the unperturbed one is just numerical diffusivity, essentially setting your mass growth. So that's why we have a converged mass growth, because of these convergence. Okay, but now I talked a lot about some technical detail. So now let's come back to our galaxies and our initial question, right? How much does it really matter for the CGM? How much cold gas at the end of the day can we bring with this mechanism into the CGM? And the first ingredient we are missing really is a more realistic wind, right? Clearly our box of, one gas flowing in isn't too realistic. So what we need is a more realistic wind profile. And we did that, and we used, famous Chevalier-Clegg solution for wind, which, density drops off, pressure drops off with radius as you would expect from an adiabatically expanding wind blown by supernovas. Now, if we parameterize our mass growth rate, just from dimensions, you can see that, it should be proportional to how much area your cold gas has, right? That's how much you can mix in, and how much density the surrounding medium has. And then the rest you can just put into some mixing velocity. Now, the interesting thing I want to just show you really quick is that, well, if the density goes down as r squared, the mass growth should also cease when the cloud is going outwards, right? But you shouldn't forget that the pressure is also dropping, and that means your whole cloud is expanding, so you end up with a higher surface area, which means a higher mass growth rate. And now this mixing velocity, due to the pressure changing, it also scales very weakly. But if you put all these things together, you find that you have a constant mass growth rate with distance. And we checked that numerically, it roughly seems to work. And that's interesting, right? We have this small cloud being ejected from the galaxy and then traveling maybe kiloparsecs and constantly keeps on growing. So, the idea...
That's like what you would call like the virial radius of the galaxy.
Sorry?
How far is that out? Like to what you would call like the virial radius of the galaxy. How far does that constant mass?
Until the Chevalier-Clegg holds. So that's...
I'm trying to like guess since it's going.
Right. No, that's a good question. We can chat about that later. That's a good question. But the basic idea is that you have some cloud that's pushed out, it's being entrained, elongated, so it has even more area. So then we have our Chevalier-Clegg wind. The cloud is constantly growing, and if you just plug in some numbers really quick, you get the mass you can bring out with this kind of mechanism into the CGM, like comparable to the stellar mass of the galaxy, which is actually quite a lot. As a side note, I want to mention that because you have constantly cold gas there, you cannot just bring cold gas out, but also maybe molecules and dust, because they hate hot gas. So if they're embedded always in cold gas, it's actually quite nice. So there's a grad student working with me, Ryan Faber, and it's a brand new result. And what he has done is to put tracer particles in the cloud. And he said, whenever gas reaches 10 to the 5 Kelvin, then my dust and my molecules, they would die. And for some of the clouds, he finds survival fractions that are unity. For some, of course, it goes down depending on what's your cooling time. So that's just I want to mention. So to sum up for this kind of mechanism, the two first questions: how does the cold gas stack there, and how does it survive? In this mechanism, if T cold mix is smaller than T cloud crush, we can make cold gas survive in the wind, and it is constantly growing. So we could bring cold gas there. Now to the third question, what is its structure? I haven't at all answered to that. But if you remembered, our nice critical ratio was T cold mix divided by T cloud crush has to be smaller than unity. And you remember that T cloud crush is a function of the cloud size, whereas T cool mix is just a function of the gas properties, right? So you can rearrange this inequality to get a critical cloud radius, and clouds larger than this radius, they should survive. And if you plug in typical numbers for ISM conditions, that corresponds to clouds being roughly 2 parsec or so. So that would be the characteristic scale of this mechanism. Yes. Okay, actually it took longer than I thought, but I want to also talk about this other mechanism. So what, we could also don't bring gas there, but we can just form it there through thermal instability. And this is a nice picture from H alpha filaments. You have around these massive galaxy NGC 1275. And so there you also have X-ray observations. So we know again, you have very hot gas and very cold gas co-spatial. And for these big halos, we think, thermal instability is very important because, well, essentially for thermal instability, what you ask, how long does a gas parcel take to cool? And then you contrast that, how long does it take to fall down back onto the galaxy where it gets heated again? So this is a simulation by Mike McCord, where color-coded, well, red is unfortunately the cold gas here, so the dense gas. But okay, so here T cool over T free fall is 10. So the cooling time is much longer than the free fall time. So you have just this nice galactic disk. You don't have any cold gas up in the CGM. And the smaller you make your cooling time compared to the free fall time, and if it's less than unity, you clearly see you get this nice multiphase structure here out in the CGM. So from a great deal of literature, we know that this thermal instability is important if T cool over T free fall is smaller than 1. Now, the interesting question is, what is the structure, once you cool your gas out of this thermal instability? And there was an extremely nice paper again by Mike McCord, who asked the question, what happens to this gas cloud? So I will talk you through this nice diagram he actually put in his paper. So let's imagine we have a large gas cloud which is cooling. It's cooling on a timescale of the cooling time, and then we lose pressure support, right? We drop our whole pressure of the whole cloud. Now, if the cloud is very large, that means the gas, it can just talk, exchange information on a timescale of the sound crossing time, right? So if the cloud is very large, the sound crossing time might be much larger than the cooling time. So the standard idea was that, it cools down to T, on a timescale of T cool, and then for a long time, the sound crossing time, it's out of pressure equilibrium and slowly contracting until it is back into pressure equilibrium. But Mike McCord had this idea that instead of going this path, what a cloud will actually do, it will fragment violently into these little pieces, and which are droplets, which are of the size CST cool. So when this basically information time and the cooling time are the same. And then, again, moving time to show you that this is really the case. This is a cloud cooling from 10 to the 5 to 10 to the 4 Kelvin. And yes, so you see it's super violent. It fragments into this many pieces. And this theory he called the shattering. Now, one of the main statements of the theory is that, yes, clouds shatter into the size of CST cool, which is 0.1 parsec for 1 centimeter per 1 particle per cubic centimeter. Sorry, that's. Now this should make you extremely suspicious, right? Because I just told you that clouds are 2 parsec in order to survive, and now I just told you that clouds are 0.1 parsec if they come out of this thermal instability. So what is it now? And the answer is, of course, as always, that it depends. So let's look a little bit closer into what this shattering mechanism really is. So here we have 2 clouds, one again much larger, where CST cool, the shattering length is much larger than, the cloud is much larger than CST cool, and at one time the cloud is roughly the size CST cool. And here you see the density projections and slices through the pressure. And if I let the cloud cool, you see here this violent stuff before, and here, it's just contracting, never loses pressure balance, because it can always talk, all the particles are in sonic contact. So just as Mike McCord said, if the cloud is much larger than CST cool, the cloud shatters. But now, let's have 2 clouds which are very large, so much larger than CST cool. And one time we let a cloud cool from 10 to the 5 to 10 to the 4 Kelvin, and one time from just above 10 to the 4 Kelvin down to 10 to the 4 Kelvin. See what happens? So this one shatters, and this one just pulsates. So it doesn't shatter. It's not as much out of pressure balance. So really the statement should be a bit longer. It should be, a cloud shatters if it's much larger than St cool, and if it's enough out of pressure balance. So if I let it cool kind of from high enough. And this, what is high enough to shatter? So here, what I show you is the size of different clouds and TCL over T floor, so how long I let it cool. And color-coded is how many clumps I end up with. So clearly these yellow dots here, that's where my simulation shattered, and the other simulations not. So you see, the cloud has to be large enough in order to shatter, but there's also some kind of boundary here. So you have to cool far enough down. And these are for overdensities, initial overdensities of 10. If I, this would be, where maybe shattering occurs. But now if I populate this parameter space with different initial overdensities, so the different symbols here correspond to different overdensities, 2, 10, or 100, you see that it's not that easy. It's in fact quite messy. So what we found is we can do change this x-axis here to chi final, and chi final is how far you can cool it down times your initial overdensity, and then it actually works much better. So you need a chi final of 300 or so in order to shatter. And just showing you that in a little bit different visualization. So here I have our initial overdensity, and this is how far we could cool it down for a fixed cloud size. And all the triangles down, that's where it shattered, and all the triangles up is where my simulations didn't shatter. So you have this clear boundary here between shattering and these pulsations. Yes. So I just want to ask, why come that you have this critical boundary at roughly, this 300? And so to visualize you this, I have two simulations here, one where this final overdensity is 200 and one where it's 400. And if I let this play, you see that both are in fact fragmenting, but in this one, I just play it again. It's kind of hard to see, sorry, but yeah. What I want to show you is that you have these little droplets, and then they merge back onto these larger clouds. So what you really have is this competition between this fragmentation and coagulation. And I can show you this a little bit better when I here plot the number of droplets as a function of time. So these are the two simulations we just saw. And we see that, once it shatters, both simulations have more than 1,000 droplets or so. But then the red line, it actually declines to less than 100 droplets because they coagulate again. And that actually explains this boundary at a given final overdensity, because clearly, you would say, the further down I cool, the more likely I shatter, right? If I drop something from this height, it breaks apart. If I drop it from a higher height, well, it definitely breaks apart. So, this is basically this ratio of TCL over T4, which is how much I put it over the pressure balance. But then you have this other thing, and that is the initial overdensity. And if you look into the growth time of your gas, that's in fact proportional to your initial overdensity. So you could say smaller clouds have a smaller mass doubling time, right? If I'm not that fat, I don't have to eat that much in order to double my weight. I don't know if it makes sense, but that's so this is why for less massive clouds, the relative strength of cooling is stronger, and that's why you essentially have this boundary at this critical number of 300. That's a hand-wavy argument, but let's go with that. I just want to quickly discuss in the end. I want to quickly discuss what implications that has for the galaxies again. This boundary between shattering and pulsations. So, for instance, how much you put it out of pressure balance, you can relate that in galactic winds through the shock jump condition, you can relate that to the Mach number of your wind, right? If you have a fast wind, you put your cold gas more out of pressure zones. And you will find that this red line here corresponds to Mach number of 4 or so. And that this actually makes a difference. I can show you these videos where I have a Mach number of 1.5, what we saw before, by the way, and a Mach number of 3. And these are projections this time, not slices. So you see, you have these tiny droplets that it disintegrates and then falls back for this lower Mach number. But for the lower Mach number, what you will end up is always some kind of solid, tail. Whereas if you compare that to a higher Mach number, it will come in a second, the whole cloud actually disintegrates in these tiny pieces, and then they fall back. So, for Mach number larger than 4 or so, and 3 is basically 4 in this argument, then these dynamic coordination effects become important. Now, for thermal instability, your initial overdensity is linear, so we are here, and that would mean that only for medium, hot medium, which is hotter than 2 times 10 to the 6 or 3 times 10 to the 6 Kelvin, then we actually end up with a fog or this mist. Otherwise, we have larger clouds of cold gas in our CGM. Right, and that's basically the two takeaway messages I wanted to give you. So first of all, we can make clouds, we can push clouds with a hot wind, and they can survive that if this T-cool mix over T-cloud crush is smaller than unity. So if the cold gas manages to entrain hot material. And if the CGM is mist-like or cloud-like, could depend on this, what I talked about this competition between shattering and coagulation. Sorry, I kind of felt that I lost most few in the last part of the talk, but I'm happy to take questions. And I'm also here tomorrow morning. If there's more questions, I'm very happy to discuss it on a blackboard or something. Thank you.